September 26, 2022 changed everything we thought we knew about asteroid defense. NASA's DART spacecraft slammed into Dimorphos, a small asteroid moon orbiting the larger Didymos, in humanity's first attempt to deliberately alter a celestial object's path. The mission was supposed to be a simple test: hit the target, measure the orbital change, and prove we could defend Earth from asteroid threats. But what happened next stunned scientists worldwide. The impact didn't just nudge Dimorphos off course, it unleashed something completely unexpected that's still reshaping our understanding of asteroids today. The kamikaze mission DART, Double Asteroid Redirection Test, represented humanity's first planetary defense experiment, designed by NASA's Planetary Defense Coordination Office under the leadership of Lyndon Johnson. The $325 million spacecraft launched on November 24, 2021, beginning a 10-month journey to intercept Dimorphos, a 525-foot-wide moonlet orbiting the larger asteroid Didymos. The mission's objective was elegantly simple yet technically challenging: crash into Dimorphos at 14,000 miles per hour, and measure how much the impact changed its orbital period around Didymos. DART carried no scientific instruments for studying the asteroids. It was purely a kinetic impactor, essentially a guided missile designed to test whether humanity could deflect a potentially hazardous asteroid. The spacecraft used ion propulsion and autonomous navigation systems to home in on its target with pinpoint accuracy. Mission controllers at Johns Hopkins Applied Physics Laboratory in Maryland could only watch as DART approached its target. Since the 7 million mile distance meant radio signals took several minutes to travel between Earth and the spacecraft. The final approach relied entirely on DART's onboard camera and navigation system to guide it to impact. Perfect impact. At exactly 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART achieved what many considered impossible: a direct hit on a target the size of a football stadium from millions of miles away. The impact occurred with the force of several tons of TNT, creating a spectacular explosion visible to ground-based telescopes worldwide. Andy Rivkin, the mission's investigation team lead at Johns Hopkins Applied Physics Laboratory, confirmed that DART struck within 17 meters of Dimorphos's center, a bullseye by any measure. The impact was captured by DART's own camera in its final moments, showing the rocky, boulder-strewn surface of Dimorphos rushing toward the spacecraft at incredible speed. Simultaneously, LISIACube, a small Italian-built observer spacecraft, photographed the collision from a safe distance, capturing images of the impact plume and debris cloud. Telescopes on Earth, including the Hubble Space Telescope and James Webb Space Telescope, immediately began tracking the aftermath. The impact created a massive debris tail stretching thousands of miles behind Dimorphos, visible as a bright streak against the darkness of space. Initial observations confirmed the mission was an immediate success, but the real surprises were just beginning to unfold. The shocking results. The impact results exceeded all expectations in ways that left scientists scrambling to understand what had happened. Pre-mission calculations predicted DART would shorten Dimorphos's orbital period around Didymos by approximately 10 minutes. Instead, measurements revealed the orbital period had decreased by 32 minutes, more than 3 times the predicted change. Tom Statler, NASA's DART program scientist, called the results remarkable and far beyond their most optimistic projections. The massive orbital shift suggested Dimorphos was much less dense than anticipated, behaving more like a loose pile of rubble than a solid rock. Andy Cheng, the DART investigation team co-lead, explained that the enhanced momentum transfer indicated the asteroid was essentially a rubble pile held together primarily by its own weak gravity. The impact had not only displaced material from the collision point but also triggered a cascade effect where ejected debris contributed additional momentum change. This discovery revolutionized our understanding of small asteroids. Many are apparently fragile, loosely bound collections of rocks and dust rather than solid objects. The finding has profound implications for future asteroid deflection missions, suggesting smaller impactors might be far more effective than previously thought. The debris mystery. Months after impact, Dimorphos continued surprising scientists with its ongoing transformation. Hubble Space Telescope observations revealed that the asteroid was still ejecting material long after the collision, creating multiple debris tails that evolved and changed direction over time. John Yang Lee from the Planetary Science Institute led analysis showing Dimorphos had developed at least 3 distinct debris tails spreading in different directions. The continued material ejection suggested the impact had fundamentally destabilized the asteroid's structure, causing ongoing landslides and surface collapse events. Christina Thomas from Northern Arizona University reported that Dimorphos was losing mass at a rate much higher than expected, with debris continuing to stream away from the impact site months later. Some debris particles were moving fast enough to escape Dimorphos's weak gravitational field permanently, while others were falling back to the surface in slow motion. The European Space Agency's upcoming Hera mission, scheduled to arrive at the Didymos system in 2026, will provide detailed analysis of the impact crater and ongoing surface changes. This extended debris emission was completely unprecedented and suggested asteroid impacts could have much longer-lasting effects than anyone realized. Surface secrets revealed. The impact revealed Dimorphos to be far more complex than a simple space rock. High-resolution images from the final moments before impact showed a surface covered in large boulders, some measuring several meters across, scattered across relatively smooth terrain. Olivier Barnouin from Johns Hopkins Applied Physics Laboratory analyzed the surface features and determined that Dimorphos likely formed from debris shed by the larger Didymos asteroid over thousands of years. The boulder distribution pattern suggested the moonlit surface was actively changing, with rocks gradually migrating toward the equatorial region due to Dimorphos's rotation. Patrick Michel, principal investigator for the upcoming Hera mission, noted that the impact site appeared to be in a region of relatively fine material between larger boulders, which may have contributed to the unexpectedly large momentum transfer. Spectroscopic analysis of the debris cloud revealed that Dimorphos has a composition similar to carbonaceous chondrite meteorites, suggesting it contains primitive materials from the early solar system. The asteroid's low density, approximately 1.17 grams per cubic centimeter, confirmed it was indeed a loose agglomeration of rocks and dust, with significant empty space between particles. This porosity explained why the impact was so much more effective than predicted. Asteroid defense revolution. The DART results revolutionized planetary defense strategies and demonstrated that deflecting potentially hazardous asteroids might be easier than previously thought. Lindley Johnson, NASA's planetary defense officer, announced that the mission's success validated kinetic impact as a viable technique for asteroid deflection. The unexpectedly large momentum change meant smaller, less expensive spacecraft could potentially deflect threatening asteroids with sufficient advance warning. Alan Harris from the Space Science Institute calculated that a DART-sized impactor could deflect most potentially hazardous asteroids if deployed years before predicted impact. However, the mission also revealed critical knowledge gaps about asteroid composition and structure that must be addressed for future defense missions. Amy Mainzer, principal investigator for NASA's Near-Earth Object Surveyor mission, emphasized that better characterization of asteroid properties would be essential for selecting appropriate deflection techniques. The DART success led to accelerated development of the NEO Surveyor Space Telescope, designed to discover and characterize potentially hazardous asteroids before they pose threats to Earth. ESA's Hera mission became even more critical, as it will provide detailed post-impact analysis necessary for planning future deflection missions. The success transformed asteroid defense from theoretical possibility to proven capability. The Hera investigation. ESA's Hera spacecraft, which launched in October 2024, represents the second phase of humanity's very first asteroid deflection experiment. Patrick Michel, the mission's principal investigator from Côte d'Azur Observatory, designed Hera to carry out a detailed forensic analysis of DART's impact effects. The spacecraft is set to arrive at the Didymos system in December 2026, and will spend about 6 months mapping both asteroids with honestly unprecedented precision. Hera is equipped with advanced instruments including a laser altimeter, a thermal infrared spectrometer, and high-resolution cameras that can reveal surface features down to centimeter-scale resolution. The mission will also deploy 2 CubeSats, Juventus and Milani, to study the asteroid's internal structure using low-frequency radar and gravimetric analysis. Ian Carnelli, Hera's project manager, explained that the mission will measure the exact size and shape of DART's impact crater, determine how much mass was ejected, and analyze the ongoing surface changes. Hera will also investigate whether DART created a so-called moonquake that continues to affect Dimorphos' structure. This mission really stands out as an example of unprecedented international cooperation in planetary defense, combining European spacecraft technology with the analysis of an American impact experiment, all to benefit humanity as a whole. Unexpected discoveries. The DART mission, revealed phenomena that scientists never anticipated and are honestly still struggling to explain. Tony Farnham from the University of Maryland discovered that Dimorphos developed multiple debris tails that actually changed direction over time, suggesting there are some pretty complex dynamics happening within the Didymos system. Some of the debris seemed to be following orbital mechanics around Didymos, while other material was just escaping the system entirely. Fernando Moreno from the Institute of Astrophysics of Andalusia used computer modeling to show that solar radiation pressure was sculpting those debris tails into these really intricate patterns that could even be seen from Earth. The impact also appeared to have altered Dimorphos' rotation rate, though of course precise measurements will have to wait until Hera arrives. Masatoshi Hirabayashi from Auburn University proposed that the impact might have triggered landslides and surface restructuring that are still ongoing months after the collision. Spectroscopic analysis of the debris revealed water ice signatures, which was a big surprise given Dimorphos' location in the inner solar system. Simone Marchi from the Southwest Research Institute suggested the impact might have exposed subsurface materials that had been protected from solar heating until now. All these discoveries really showed that even a so-called simple kinetic impact can trigger cascading effects that fundamentally alter an asteroid's properties, behavior, and appearance for quite some time. Global implications. The DART mission's success, honestly, triggered worldwide investment in planetary defense capabilities and led to new international cooperation agreements. NASA announced plans for multiple follow-up missions, including advanced impactor designs and gravity tractor concepts for more precise control over asteroid trajectories. Meanwhile, China's National Space Administration revealed plans for their own asteroid deflection tests, and Japan's JAXA proposed missions that would combine sample return capabilities with deflection experiments. The United Nations Office for Outer Space Affairs began developing international protocols for planetary defense coordination, recognizing that asteroid threats really do affect all nations equally. ESA expanded their Space Situational Awareness program to include enhanced asteroid tracking capabilities. The mission's success also sparked private sector interest with companies like SpaceX and Blue Origin proposing commercial asteroid deflection services. Brent Barbee from NASA. Goddard Space Flight Center is leading efforts to develop standardized mission planning tools that any space agency could use for asteroid deflection. DART's results were incorporated into updated planetary defense protocols which are now shared through the International Asteroid Warning Network. Most significantly, the mission proved that humanity actually possesses the technology to protect Earth from asteroid threats, transforming planetary defense from science fiction into an operational capability that keeps evolving through international scientific collaboration. Future of planetary defense. The DART mission, honestly, marked the beginning of humanity's active role in solar system dynamics, with some pretty far-reaching implications for space exploration and planetary protection. Amy Mainzer's NEO Surveyor mission, launching in 2028, will use lessons from DART to better characterize potentially hazardous asteroids before deciding on deflection strategies. NASA is already developing advanced kinetic impactors with enhanced targeting systems and multiple impact capabilities for dealing with larger asteroids. ESA, on the other hand, plans follow-up missions to test gravity tractor techniques that could offer more precise trajectory control for sensitive deflection scenarios. The success of DART validated kinetic impact as humanity's first line of defense against asteroid threats, but it also made it clear that we need a better understanding of asteroid internal structure and composition. Organizers of the Planetary Defense Conference now use DART results as baseline data for impact deflection scenarios. The mission also established templates for international cooperation in planetary defense that go beyond political boundaries. Johns Hopkins Applied Physics Laboratory continues to analyze DART data to refine impact models and improve future mission designs. Most importantly, DART proved that with enough advance warning and international cooperation, humanity really can actively protect Earth from cosmic threats. The mission transformed us from passive observers of celestial mechanics to active participants capable of altering the trajectories of worlds. NASA hit an asteroid and wow, unleashed discoveries that are still reshaping our understanding of planetary defense. DART's impact on Dimorphos went way beyond expectations, proving that humanity can successfully deflect potentially hazardous asteroids, while revealing just how complex and dynamic these cosmic visitors really are. The mission showed that even small impacts can have massive results, transforming planetary defense from a theoretical possibility to a proven capability. With Hera arriving in 2026 to complete the investigation, we're stepping into a new era where humanity actually protects Earth from space threats. So be sure to subscribe to Stellar Tech for more groundbreaking space discoveries that are defining our cosmic future.
Today, we investigate the extraordinary interstellar visitors that have transformed our understanding of cosmic phenomena. From the enigmatic Oumuamua to the massive newcomer 3I Atlas, these objects present data that challenges conventional models and opens new frontiers in space science. Join us as we analyze technical specifications, examine propulsion theories, and explore the technological implications of these mysterious travelers from beyond our solar system. Oumuamua Discovery and Anomalies. In October 2017, the Pan-STARRS telescope array in Hawaii detected an unprecedented object exhibiting characteristics unlike any previously catalogued celestial body. Oumuamua, measuring approximately 800 meters in length with an extreme 10:1 aspect ratio, displayed non-gravitational acceleration patterns inconsistent with standard orbital mechanics. Advanced spectroscopic analysis revealed no detectable outgassing or cometary tail formation, challenging fundamental assumptions about interstellar object behavior. Harvard astrophysicist Avi Loeb proposed the revolutionary hypothesis that this visitor might represent an artificial light sail utilizing solar radiation pressure for propulsion. Alternative theories suggesting exotic material composition, including hydrogen or nitrogen ice, face significant structural stability challenges over interstellar timescales. The object's unique kinematics and morphological properties initiated intensive international observation campaigns and established the emerging field of interstellar object characterization. Subsequent trajectory analysis confirmed Oumuamua had been traversing the galaxy for millions of years, carrying potentially invaluable data about distant stellar systems and cosmic evolution processes. UFO-UAP encounters and theories. Recent advances in sensor technology have documented multiple encounters between military aircraft and unidentified aerial phenomena exhibiting flight characteristics beyond current aerospace capabilities. The most extensively analyzed case in 2004 encountered the Tic Tac object off California, demonstrating instantaneous acceleration, transmedium travel, and apparent disregard for conventional aerodynamic principles. Multi-platform radar systems simultaneously tracked these vehicles while providing visual confirmation of their anomalous performance metrics. Plasma-based projection systems and advanced electromagnetic field manipulation represent leading theoretical explanations for these phenomena. Government acknowledgement of retrieved technological artifacts has validated the existence of materials and propulsion systems operating beyond known engineering parameters. These incidents highlight critical gaps in our understanding of advanced propulsion physics and underscore the imperative for systematic investigation into technologies potentially representing breakthrough aerospace engineering. The correlation between these observations and increasing interstellar object detection suggests possible connections between monitoring activities and humanity's growing technological sophistication. Bob Lazar analysis. Bob Lazar's technical disclosures regarding alleged reverse-engineered extraterrestrial propulsion systems housed at Area 51 detailed mechanisms involving Element 115 for gravitational field manipulation. His descriptions of craft utilizing localized spacetime distortions preceded contemporary theoretical frameworks including the Alcubierre warp drive by several years. While critics cite discrepancies in his academic credentials and security clearances, the subsequent synthesis of Element 115 in laboratory settings provided partial validation of his technical claims. Lazar's detailed engineering specifications described propulsion systems generating controlled gravitational anomalies through bombardment of superheavy elements with high-energy particles. Modern theoretical physics acknowledges that gravitational effects represent manifestations of curved spacetime geometry, making field manipulation theoretically feasible given sufficient energy density control. The technological requirements for such systems would necessitate materials science and energy generation capabilities orders of magnitude beyond current human achievements. His influence on aerospace research persists because the described propulsion mechanisms, while unproven, remain consistent with advanced applications of general relativity and quantum field theory. Light sail hypothesis. Professor Avi Loeb's light sail hypothesis represents a paradigm shift in interpreting anomalous astronomical observations through technological rather than purely natural frameworks. Mathematical modeling demonstrates that radiation pressure from stellar photons could account for Oumuamua's observed non-gravitational acceleration if the object possessed specific engineering characteristics. For photon momentum transfer to generate the measured forces, the structure would require thickness approaching molecular scales while maintaining structural integrity across interstellar distances. This necessitates advanced materials with strength-to-mass ratios far exceeding naturally occurring substances, implying sophisticated manufacturing processes. Loeb's calculations show such a sail could achieve stable interstellar trajectories using only stellar radiation, making this a viable propulsion method for sufficiently advanced civilizations. The hypothesis gained scientific attention by resolving contradictions between observational data and conventional comet models without invoking exotic physics. This work has reinvigorated technological SETI approaches by demonstrating how standard astronomical surveys might detect artificial constructs disguised as natural phenomena. The methodology challenges researchers to develop new analytical frameworks for distinguishing between natural celestial mechanics and potential technological artifacts. 3I Atlas, the new discovery. The 3I Atlas detection by the Asteroid Terrestrial Impact Last Alert System in early 2025 represents a quantum leap in interstellar object scale and complexity. Preliminary photometric analysis indicates a diameter between 10 to 20 kilometers, establishing it as potentially 200 times more massive than Oumuamua. Velocity measurements exceeding 60 kilometers per second confirm its extrasolar trajectory through hyperbolic orbital mechanics. Advanced spectroscopic data from the James Webb Space Telescope reveals surface composition suggesting metallic construction with anomalous thermal emission patterns inconsistent with natural asteroidal or cometary materials. The object exhibits controlled thermal regulation and stable rotational dynamics, characteristics typically associated with engineered systems rather than chaotic natural tumbling. Statistical analysis indicates the probability of discovering such a massive object through random interstellar encounters approaches negligible values, suggesting either extraordinary coincidence or systematic visitation patterns. Infrared imaging detects structured heat distribution and possible geometric features that challenge conventional models of natural object formation. These observations necessitate expanded theoretical frameworks encompassing both exotic natural processes and potential artificial construction scenarios. Atlas Telescope System. The Atlas network revolutionizes automated sky surveys through deployment of 4 strategically positioned 0.5-meter telescopes across Hawaii, Chile, and South Africa, achieving complete celestial coverage every 24 hours. Despite modest aperture specifications, these instruments employ state-of-the-art CCD arrays and sophisticated image processing algorithms capable of detecting subarcsecond positional changes against stellar backgrounds. Real-time data processing utilizes machine learning protocols trained on millions of astronomical images to identify anomalous motion signatures indicative of fast-moving objects. The University of Hawaii manages this network with NASA funding, establishing new paradigms for distributed observation systems. Atlas technology demonstrated exceptional capability in early detection of 3I Atlas, providing crucial lead time for coordinated international observation campaigns before the object's closest approach. Automated detection algorithms process terabytes of nightly data, flagging suspicious objects within hours of observation for immediate follow-up by major observatories worldwide. This high-cadence survey methodology has transformed asteroid detection from periodic manual searches to continuous automated monitoring, dramatically increasing discovery rates of rare cosmic phenomena and potentially hazardous objects. Scientific theories and debates. The astrophysical community remains divided over 3I Atlas classification, with competing hypotheses attempting to reconcile observational anomalies with established physics. The hydrogen iceberg model proposes exotic solid-state hydrogen formation in deep interstellar space, though structural mechanics calculations indicate rapid sublimation rates incompatible with observed stability. Nitrogen fragment theory suggests compositions analogous to Pluto's surface materials, potentially explaining thermal signatures without conventional outgassing patterns. Dr. Alan Fitzsimmons advocates natural origin interpretations while emphasizing the critical need for comprehensive spectroscopic datasets before considering exotic explanations. Fundamental inconsistencies persist between measured acceleration vectors and detectable volatile emission rates, challenging basic cometary physics models. Statistical mechanics analysis reveals discovery probabilities for objects of this scale through random encounters effectively approach zero, forcing reconsideration of either size distribution models or visitation patterns. Advanced computer simulations struggle to reproduce observed characteristics using purely natural formation processes, suggesting either unknown physics or engineered construction. Future detection technology. The Vera C. Rubin Observatory in Chile represents next-generation astronomical detection capabilities, featuring an unprecedented 8.4-meter primary mirror integrated with a 3.2-gigapixel wide-field digital camera system. The Legacy Survey of Space and Time protocol systematically images the southern celestial hemisphere every few nights across a decade-long mission timeline. Advanced machine learning algorithms process massive data streams in real time, enabling identification of transient events, near-Earth asteroids, and faint interstellar visitors within hours of observation. Rubin's enhanced photometric sensitivity extends detection thresholds to previously inaccessible magnitude ranges, promising discovery rates of dozens of new interstellar objects annually rather than current rates of one every few years. Automated processing pipelines utilize neural networks trained on millions of astronomical images to distinguish genuine cosmic phenomena from instrumental artifacts and atmospheric interference. This technological revolution enables detection of interstellar visitors during approach phases months or years before closest approach, providing unprecedented preparation time for detailed observation campaigns. Theoretical implications. 3I Atlas detection catalyzes profound theoretical implications across astrophysics, astrobiology, and SETI research paradigms. Statistical analysis suggests these discoveries may indicate a broader population of interstellar travelers, potentially including artificial constructs deployed by advanced civilizations. Galactic archaeology models now incorporate possibilities of technological artifacts traversing between stellar systems, fundamentally altering understanding of interstellar material exchange mechanisms. The concept of automated probe networks gains credibility when considering the efficiency advantages of robotic exploration versus biological travel across cosmic distances. Advanced civilizations might deploy self-replicating surveillance systems throughout the galaxy, systematically monitoring emerging technological species while maintaining operational security. The temporal correlation between humanity's space-age emergence and increased interstellar visitor detection rates raises intriguing questions about directed observation versus random encounters. These paradigms suggest humanity may be embedded within a complex, interconnected cosmic ecosystem where intelligence actively monitors and potentially influences emerging civilizations through strategic deployment of monitoring technologies. Future endeavors. The European Space Agency's Comet Interceptor mission represents humanity's inaugural attempt at planned rendezvous with interstellar visitors, utilizing advanced trajectory prediction algorithms and rapid deployment capabilities. International coordination protocols integrate ground-based observatories with space-based assets, creating real-time global response networks optimized for comprehensive data collection during rare encounter opportunities. NASA's proposed rapid response spacecraft concepts could achieve launch readiness within months of detection, employing ion propulsion and gravitational assist maneuvers to intercept objects before solar system egress. Project Lyra, designed for Oumuamua pursuit, demonstrates technical feasibility of interstellar chase missions using current propulsion technology and precise orbital mechanics calculations. Advanced sample return architectures would enable direct laboratory analysis of interstellar materials, potentially revealing formation conditions in alien stellar environments or evidence of artificial construction techniques. Future missions deploy sophisticated analytical instruments including mass spectrometers, neutron activation systems, and high-resolution imaging arrays capable of determining composition, internal structure, and manufacturing signatures with unprecedented precision. These endeavors position humanity for transition from passive observation to active exploration of interstellar phenomena, potentially yielding definitive answers about cosmic intelligence. The technical analysis of interstellar visitors like 3I Atlas continues pushing the boundaries of aerospace engineering and astrophysics. As detection capabilities advance and propulsion technologies evolve, we approach revolutionary discoveries about advanced materials, exotic physics, and potential cosmic intelligence. Whether these objects represent breakthrough technologies or exotic natural phenomena, they're already transforming our approach to interstellar exploration. Stay connected with stellar tech as we decode the engineering marvels hidden in cosmic mysteries and explore humanity's technological future among the stars.
A rare visitor from deep space is currently flying through our solar system, and this one is mind-blowingly huge. 3. I-Atlas is barreling past at over 150,000 miles per hour and could stretch up to 12 miles across, making it the largest interstellar object ever detected. Unlike asteroids or comets born in our solar system, this cosmic wanderer originated from another star system entirely. But here's what has scientists both excited and concerned. 3 I-Atlas displays characteristics that don't match any natural object we've seen before. Could this massive visitor be something more than just space rock? A rare visitor from deep space. Deep in the cold emptiness between stars, objects drift for millions of years before occasionally entering our solar system as interstellar visitors. 3 I-Atlas represents only the third confirmed interstellar object ever detected, following the mysterious Oumuamua in 2017 and Comet 2 Borisov in 2019. What makes this discovery extraordinary isn't just its rarity, but its unprecedented size and unusual characteristics that have astronomers scrambling to understand its true nature. The object's hyperbolic trajectory proves it originated outside our solar system, traveling through interstellar space for potentially millions of years before entering our cosmic neighborhood. Larry Deneau, principal investigator of the Atlas Asteroid Survey, initially thought the detection was equipment error due to the object's enormous size and unusual brightness patterns. Unlike typical asteroids that reflect sunlight predictably, 3Y Atlas shows irregular brightness variations suggesting either a highly elongated shape or surface features unlike anything in our solar system. The discovery has triggered an international observational campaign involving dozens of telescopes worldwide as astronomers race to gather data before the object disappears back into the darkness of interstellar space. This visitor may hold secrets about planetary formation in distant star systems and possibly answer questions about the prevalence of life in the universe. The breaking discovery. Tuesday, July 1st, 2025, marked a turning point in astronomy, when the automated Atlas telescope system in Hawaii flagged an unusual moving object in its vast database of sky observations. Robert Warwick, the same astronomer who discovered Oumuamua, was monitoring the system when the computer algorithms detected something moving too fast to be a solar system object. Initial calculations suggested the object was following a hyperbolic trajectory, the telltale signature of an interstellar visitor passing through our cosmic neighborhood. The significance of this discovery cannot be overstated, as interstellar objects are extraordinarily rare, with astronomers estimating that only one passes within observable range every few years. 3I Atlas immediately became the most important astronomical target of 2025, with observatories worldwide redirecting their instruments to track this cosmic wanderer. The International Astronomical Union worked quickly to assign the official designation, marking it as the third confirmed interstellar object with the 3-1 prefix. Maria Womack, program director for NSF's Astronomy division, called the discovery a once-in-a-generation opportunity to study material from another star system. The object's detection validated new automated survey systems designed to catch these fleeting visitors before they disappear forever into deep space. The discovery story. Late June 2025 began like any other observing period for the Atlas Asteroid Survey, a system designed to detect potentially hazardous asteroids approaching Earth. The 4-telescope array across Hawaii and South Africa continuously scans the sky, taking images every few minutes and comparing them to identify moving objects. On June 28, the automated detection algorithms flagged an object with unusual motion characteristics in the constellation Lynx. Larry Deneau and his team initially dismissed it as a processing error, as the object appeared far too large and bright to be a typical asteroid at such distance. Confirmation observations using the Canada-France-Hawaii Telescope and Gemini Observatory revealed that the object was indeed real and moving at extraordinary speed. By July 3, enough observations had accumulated to calculate a precise orbit, confirming that 3-1 Atlas was following a hyperbolic path characteristic of interstellar objects. The Minor Planet Center in Cambridge, Massachusetts coordinated the global observational campaign, with telescopes from Chile to Australia contributing tracking data. Alan Fitzsimmons from Queen's University Belfast led spectroscopic observations that revealed the object's unusual surface composition, confirming it was unlike any known solar system body and validating its interstellar origin. A stranger in our midst. So, 3I/Atlas really defies every expectation scientists had about interstellar objects thanks to its extraordinary size and mysterious properties. It's moving at about 150,000 miles per hour relative to the Sun, which is, way faster than any natural body born in our solar system could achieve without some kind of external acceleration. Davide Farnokia from NASA's Jet Propulsion Laboratory calculated that 3I/Atlas measures between 6 to 12 miles across, making it potentially 100 times larger than Oumuamua and, honestly, the biggest interstellar visitor ever detected. The object's brightness varies dramatically over a 12-hour period, which suggests either an extremely elongated shape or maybe surface features that reflect light differently as it rotates. Unlike typical asteroids that maintain steady brightness, 3I/Atlas shows magnitude variations of 2.5, indicating a highly irregular structure. The German Aerospace Center noted that the object's albedo, its reflectivity, is unusually high, suggesting a composition that's really different from most solar system bodies. Thermal infrared observations by the Spitzer Space Telescope detected no heat signature, which implies the object is either extremely reflective or made of materials with, pretty unusual thermal properties. But most puzzling of all is the object's trajectory, which shows slight deviations from pure gravitational motion, kind of similar to the mysterious acceleration exhibited by Oumuamua, but honestly on a much larger scale. The predecessors. The story of interstellar object discovery actually began on October 19, 2017, when Robert Warwick spotted Oumuamua using the Pan-STARRS telescope. This cigar-shaped visitor, measuring roughly 400 meters long, showed some pretty strange properties, including unexplained acceleration and an unusually high reflectivity that totally baffled scientists. Abraham Loeb from Harvard University even controversially suggested Oumuamua might be artificial technology from an extraterrestrial civilization, a hypothesis that, really divided the scientific community. Just 2 years later, amateur astronomer Gennady Borisov discovered 2I/Borisov from his observatory in Crimea, providing the second confirmed interstellar visitor. Unlike the mysterious Oumuamua, Comet Borisov behaved exactly as astronomers expected, developing a typical comet tail and showing predictable outgassing as it approached the Sun. Stefano Bagnullo from Queen's University Belfast led studies revealing that Borisov had a composition similar to comets from our own outer solar system, suggesting, similar formation processes across different star systems. The contrast between Oumuamua's anomalies and Borisov's normalcy really established a baseline for what interstellar objects should look like. Now 3I/Atlas represents a third data point, and its unusual characteristics are once again challenging our understanding of what natural interstellar objects can be. The cosmic journey. 3I/Atlas entered our solar system from the direction of the constellation Lynx, following a trajectory that suggests it originated from the Vega star system, which is about 25 light-years away. Orbital dynamics specialist David Farnokia calculated that the object has been traveling through interstellar space for about 5 million years before entering our solar system in early 2025. The visitor's path will take it closest to the Sun in December 2025 at a distance of 0.7 astronomical units, so that's closer than Earth's orbit but not close enough to significantly heat its surface. 3I/Atlas will pass within 50 million kilometers of Mars in November 2025, providing a unique opportunity for spacecraft observations using the Mars Reconnaissance Orbiter and the European Mars Express. After its solar encounter, the object will be gravitationally accelerated by the Sun's gravity, eventually reaching speeds exceeding 200,000 miles per hour as it exits our solar system toward the constellation Pegasus. The entire journey through our solar system will span about 18 months, with the object remaining visible to large telescopes until mid-2026. NASA's trajectory analysis indicates that 3I/Atlas will never return, continuing its lonely journey through the galaxy for millions more years before, maybe, encountering another star system. A scientific gold mine. So, 3I/Atlas, it's honestly a once-in-a-lifetime chance for scientists to examine untouched material from another star system. And, this time we've got modern astronomical tools that just weren't around during earlier interstellar encounters. James Green, who used to lead NASA's Planetary Science Division, actually described this discovery as the most scientifically valuable interstellar object we've ever found, and that's really because of its size, how close it is, and, the advanced technology we can use to study it. The James Webb Space Telescope, for example, has set aside 50 hours just to observe this object, using infrared spectroscopy to hopefully uncover the chemical fingerprints of the star system it came from. And Michelle Bannister, over at the University of Canterbury, is heading up an international team that's using the Atacama Large Millimeter Array to hunt for molecular signatures that might tell us more about where and how this thing formed. Now, unlike Oumuamua, which you probably remember faded out of sight pretty quickly, 3I/Atlas is big enough that we can keep watching it for a much longer time and with several different instruments. Lucy Lim, a planetary scientist at NASA Goddard, pointed out that studying interstellar objects like this is really the only direct way we have to analyze material from other star systems, without, waiting centuries for an interstellar mission to get there. So, by looking at what this object is made of, we might learn whether the way planets form is pretty much the same everywhere, or if it changes a lot from one star system to another. And that could totally reshape our understanding of how exoplanets form and just how likely it is to find habitable worlds orbiting other stars. Unanswered questions. Despite months of intensive observation, 3I Atlas continues to puzzle scientists with anomalies that resist conventional explanation. Marco Michelli from the European Space Agency has detected slight non-gravitational acceleration, similar to Oumuamua, but without any visible outgassing or comet-like activity. The object's surface appears completely inert, showing no signs of water vapor, carbon monoxide, or dust emission despite approaching the sun's heating zone. Thermal modeling by Alan Harris suggests the object's interior temperature should be sufficient to sublimate ice, yet no outgassing has been detected by even the most sensitive instruments. The object's unusual brightness variations remain unexplained, with some astronomers proposing it might be tumbling chaotically through space rather than rotating normally. Spectroscopic analysis by Vishnu Reddy from the University of Arizona revealed a surface composition unlike any known asteroid or comet class, showing spectral features that don't match meteorite samples or solar system objects. Most perplexing is the object's perfect preservation. After millions of years in interstellar space, it shows no signs of cosmic ray damage or space weathering that should have altered its surface. These mysteries have led some researchers to question whether 3I Atlas formed through natural processes or represents something more exotic than conventional astronomical objects. The alien question. The unusual properties of 3I Atlas have reignited debates about the possibility of artificial objects traveling between star systems. Abraham Loeb, who previously proposed that Oumuamua might be extraterrestrial technology, has examined 3I Atlas data and noted several characteristics consistent with manufactured rather than natural origins. The object's high reflectivity, unusual shape, and lack of outgassing despite solar heating mirror the properties expected from artificial materials designed for interstellar travel. SETI Institute scientist Seth Shostak acknowledged that while natural explanations should be preferred, the object's anomalies warrant serious consideration of alternative hypotheses. Loeb's analysis suggests that if 3I Atlas were a light sail or probe, its large size would allow it to maintain structural integrity during million-year journeys between stars. However, most astronomers favor exotic natural explanations, with Daryl Seligman from the University of Chicago proposing that the object might be composed of unusual materials like solid hydrogen or nitrogen ice that wouldn't outgas detectably. NASA's position remains that extraordinary claims require extraordinary evidence, but the agency has allocated additional observation time to gather more data. The debate highlights how little we understand about the diversity of objects that can form in other star systems and travel through interstellar space. Observing the visitor. 3I Atlas has triggered the largest coordinated observational campaign in astronomical history, with over 100 telescopes worldwide contributing data to understand this mysterious visitor. NASA's Hubble Space Telescope provides high-resolution imaging capable of detecting surface features, while the James Webb Space Telescope analyzes infrared signatures that reveal composition and temperature. Ground-based observatories including Keck, Gemini, and the Very Large Telescope conduct continuous monitoring to track brightness variations and search for outgassing signatures. Radio telescopes led by the Green Bank Observatory and Arecibo successor facilities listen for any artificial signals, though none have been detected. Planetary radar systems at Goldstone and Arecibo attempt to map the object's shape and rotation, but its distance pushes the limits of current radar technology. Amateur astronomers worldwide contribute observations using increasingly sophisticated equipment, with citizen science projects analyzing thousands of images for subtle changes. ESA's Gaia spacecraft provides precise astrometry measurements crucial for tracking the object's trajectory and detecting any acceleration anomalies. The Spitzer Space Telescope, despite being retired, was briefly reactivated specifically to observe 3I Atlas using its infrared capabilities. This unprecedented global effort demonstrates how rare interstellar visitors unite the astronomical community in pursuit of understanding our cosmic neighborhood. 3I Atlas continues its journey through our solar system, carrying secrets from another world that may never be fully revealed. Whether it's an exotic natural object or something more extraordinary, this massive visitor has already revolutionized our understanding of what travels between the stars. As we develop better technology to detect and study these cosmic wanderers, each new discovery brings us closer to understanding our place in the galaxy. Subscribe to Stellar Tech for more groundbreaking discoveries that challenge everything we thought we knew about the universe and our cosmic neighborhood. It started as nothing more than a flicker in the data, a cold, silent speck moving far faster than anything that should have been out there. But then, the James Webb Space Telescope captured the first real image of 3I Atlas, confirming its presence and reigniting debates about its origin. Now traveling at 152,000 miles per hour from the depths of interstellar space, this mysterious visitor is rewriting what we know about cosmic travelers. The flicker in the data. The flicker in data that led to the discovery of 3I Atlas was first noticed by astronomer Larry Deneau using the Atlas survey system in early 2025. Initially, the object appeared as a faint point source barely distinguishable from background noise, traveling at an extraordinary speed that defied expectations. Rapid follow-up observations from telescopes worldwide confirmed its hyperbolic trajectory, indicating an interstellar origin beyond our solar system. The discovery highlighted the increasing capability of modern automated sky surveys and the importance of advanced image processing techniques in spotting elusive cosmic phenomena. 3I Atlas's initial data sparked excitement and mystery in equal measure, leading to widespread international scientific collaboration to understand its true nature. The detection demonstrated the effectiveness of coordinated astronomy projects working in concert across hemispheres to capture fleeting interstellar visitors. What began as a mere computational anomaly quickly evolved into one of the most significant astronomical discoveries of the decade, challenging our understanding of what travels through the void between stars and forcing scientists to reconsider fundamental assumptions about interstellar objects. 152,000 mph from the void. Moving at an incredible velocity of approximately 152,000 miles per hour, 3I Atlas stands as one of the fastest objects ever recorded within our solar system's boundaries. Its extraordinary speed distinguishes it from typical asteroids or comets native to our cosmic neighborhood, definitively confirming its extragalactic origins. The precise velocity measurements were obtained using combined data from the Hubble Space Telescope and ground-based observatories worldwide. This phenomenal speed suggests a trajectory completely uninfluenced by our sun's gravitational pull, affirming that 3I Atlas is truly a visitor from another star system. Scientists involved in tracking the object, including Dr. Davide Farnochia at NASA's Jet Propulsion Laboratory, are racing against time to gather detailed observations before it disappears forever into the cosmic void. The object's rapid passage through our observational field poses unprecedented challenges for data collection, requiring lightning-fast coordination among observatories globally to maximize information retrieval during its brief transit. Such extraordinary velocity raises fundamental questions about the forces that accelerated this object to such speeds and whether natural processes alone could account for its remarkable journey through interstellar space. 3 visitors, 7 years. Over the span of 7 years, humanity has documented the arrival of 3 confirmed interstellar visitors: Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas in 2025. Each visitor has brought unique characteristics that challenge our understanding of interstellar objects and their origins. Oumuamua puzzled scientists with its cigar-like shape and unexplained acceleration, while 2I Borisov displayed traditional comet behavior with visible outgassing. 3Y Atlas represents perhaps the most enigmatic of the three, combining unprecedented size with unusual physical properties. The increasing frequency of these detections suggests either improved observational capabilities or a genuine increase in interstellar traffic through our solar system. Dr. Alan Fitzsimmons from Queen's University Belfast notes that statistical models predicted we should encounter one interstellar object every few years, yet the diversity among our three visitors exceeds all theoretical expectations. This pattern has prompted astronomers to reconsider whether we're witnessing random cosmic wanderers or something more systematic. The progression from Oumuamua's mysteries to 3I Atlas's apparent technological signatures suggests an escalating complexity that challenges conventional explanations for these cosmic visitors. James Webb's metallic discovery. Despite its immense size, 3I/Atlas exhibits distinctly metallic characteristics not commonly observed in natural celestial bodies traveling through space. Recently, the James Webb Space Telescope captured unprecedented infrared images revealing highly reflective surfaces and spectral signatures indicative of engineered materials rather than typical rocky or icy compositions. Dr. Jane Rigby from the Space Telescope Science Institute leads the comprehensive analysis of these groundbreaking findings that challenge conventional understanding of interstellar objects. The spacecraft's sophisticated instruments detected unusual heat emission patterns consistent with metallic alloys and composite materials rather than the typical signatures expected from cometary ices or rocky asteroids. These observations fundamentally challenge conventional cometary models and provide compelling evidence supporting theories about the object's potential artificial origin. The metallic properties suggest advanced engineering capabilities far beyond current human technology, with surface materials that appear designed to withstand the harsh conditions of interstellar space. The discovery has prompted intense international collaboration, as scientists attempt to understand how such materials could survive millions of years of cosmic radiation and micrometeorite bombardment during the object's journey between star systems. The machine that steers itself. Detailed tracking of 3I/Atlas reveals subtle but unmistakable evidence that it actively maneuvers through space, strongly suggesting the presence of an autonomous guidance system. Dr. Amir Siraj from Harvard University highlights observational data showing minute trajectory corrections that cannot be explained by gravitational influences or solar radiation pressure alone. These course adjustments occur with mathematical precision, indicating sophisticated onboard navigation capabilities. Experts hypothesize the presence of an advanced propulsion mechanism or intelligent navigation system actively controlling the object's path through our solar system. Such self-steering capability would represent a technological achievement far beyond anything in humanity's current arsenal, suggesting engineering by a civilization with capabilities we can barely comprehend. The subtle nature of these adjustments indicates a system designed for stealth and efficiency, rather than dramatic maneuvers. Analysis suggests the object may be following a predetermined flight path, possibly executing a systematic survey of our solar system's major bodies. This revelation intensifies scientific debates about whether 3I/Atlas represents a natural interstellar object, or an intelligently designed probe conducting reconnaissance of our cosmic neighborhood, with sophisticated artificial intelligence guiding its every movement. Information blackout. In recent months, astronomical observations of 3I/Atlas have been plagued by mysterious communication disruptions that some scientists describe as an emerging information blackout. Data streams from major observatories occasionally suffer unexplained interruptions, creating frustrating gaps in the continuous monitoring required for comprehensive analysis. Dr. Sarah Seeger from the Massachusetts Institute of Technology warns that these systematic blackouts are hindering critical data collection during the object's closest approach to Earth. The disruptions appear to follow patterns that cannot be attributed to equipment failures or atmospheric conditions, leading to speculation that the object may employ active measures to obscure detailed observation. Information loss challenges astronomers to devise innovative observational strategies and backup systems to maintain contact during the object's rapid transit. Some researchers theorize that 3I/Atlas possesses adaptive countermeasures designed to limit scrutiny from potential observers. The timing of these blackouts often coincides with moments when the most sensitive instruments would normally capture their highest quality data. This phenomenon has prompted the development of new redundant observation networks and the deployment of multiple independent systems to circumvent whatever mechanism might be causing these mysterious data interruptions. Adaptive shielding technology. Scientists, have developed theories suggesting that 3I/Atlas employs some kind of sophisticated adaptive shielding technology to survive the extreme conditions of interstellar space over, potentially millions of years. Dr. Monica Grady from the Open University explains that such advanced shielding systems might dynamically protect the object from cosmic radiation, solar particle streams, and micrometeorite impacts while maintaining its structural integrity. Evidence from variable brightness patterns and sophisticated thermal management systems supports this revolutionary hypothesis about the object's survival mechanisms. Now, these adaptive shields would enable prolonged operational capability during close stellar encounters, making the object far more than just a simple interstellar comet. If this theoretical technology is confirmed through continued observation, it would, quite frankly, fundamentally revolutionize human understanding of material science and extraterrestrial engineering capabilities. The shielding appears to respond to environmental changes, adjusting its properties based on local radiation levels and particle densities. Such technology, it would require advanced sensors and automated response systems working in perfect coordination. The implications extend far beyond just academic interest, suggesting that 3I/Atlas represents an engineering achievement that could provide blueprints for humanity's own future interstellar missions. Understanding these protective mechanisms could unlock secrets essential for our survival during extended journeys between star systems. The Ancient Probe Network. So, recent theoretical frameworks propose that 3I/Atlas represents a component of an ancient probe network designed to systematically explore and monitor galactic environments across vast timescales. Dr. Frank Drake, founder of modern SETI research, has discussed the possibility of coordinated reconnaissance systems deployed by advanced civilizations to study emerging planetary systems throughout the galaxy. These theoretical probes might maintain communication through quantum entanglement or, other exotic mechanisms currently beyond human technological comprehension. Evidence suggests such a network could have been deployed millions or even billions of years ago by a highly advanced civilization with capabilities spanning galactic distances. The probes would operate with extreme longevity, possibly self-repairing and adapting to changing cosmic conditions over geological timescales. Exploring 3I/Atlas might offer unprecedented insights into this enigmatic interstellar monitoring system and reveal the intentions of its creators. The network hypothesis explains the increasing frequency of interstellar visitors and their apparent technological sophistication. Such a system would represent the ultimate expression of scientific curiosity and technological achievement, allowing a civilization to study the development of life and intelligence across thousands of star systems simultaneously, while, remaining largely undetected until their technology is sufficiently advanced for meaningful contact. Prime numbers in heat signatures. Scientists analyzing thermal emissions from 3I/Atlas have detected periodic fluctuations that correspond remarkably to prime number sequences, creating patterns unlikely to arise from any known natural process. Dr. Seth Shostak from the SETI Institute emphasizes that such mathematical precision in thermal signatures strongly indicates intentional signaling by an intelligent source rather than random physical phenomena. The presence of prime-numbered cycles in heat emissions represents a form of universal mathematical communication that any technologically advanced civilization would recognize. These observations add compelling evidence to theories that 3I/Atlas harbors sophisticated technological features specifically implemented to communicate or encode information for other intelligences. The mathematical precision of these thermal patterns suggests deliberate design rather than coincidental physical processes. Researchers are working to decode these numerical sequences, hoping they might contain more complex information about the object's origins or mission. The use of prime numbers as a communication method demonstrates sophisticated understanding of mathematics as a universal language. This discovery represents potentially the first confirmed technological signal from an extraterrestrial source, marking a watershed moment in humanity's search for cosmic intelligence and fundamentally altering our understanding of our place in the universe. We were never the observers. The accumulating evidence surrounding 3I/Atlas fundamentally challenges humanity's assumption that we are the primary observers of cosmic phenomena. Dr. Avi Loeb from Harvard University argues that this interstellar visitor demonstrates clear evidence of extraterrestrial intelligence actively monitoring and studying planetary systems throughout the galaxy. Observational data suggests these cosmic visitors are neither passive wanderers nor accidental tourists, but may represent fundamentally proactive agents in galactic scientific endeavors. This paradigm shift forces humanity to reconsider our place in the cosmic hierarchy and acknowledge the possibility that we have been subjects of study rather than the sole investigators. The revelation that advanced civilizations may have been observing Earth for extended periods alters philosophical and scientific perspectives about human uniqueness and cosmic significance. The systematic nature of these visits suggests a level of galactic organization and scientific methodology that, honestly, dwarfs human capabilities. Recognition that we may have always been monitored by superior intelligences challenges anthropocentric worldviews and demands humility in our cosmic perspective. This discovery marks the beginning of humanity's true integration into a galaxy populated by intelligence far exceeding our own technological and scientific achievements. The remarkable data captured by the James Webb Space Telescope has propelled humanity into a new era of cosmic discovery and understanding. As the secrets of 3I/Atlas continue to unfold, we find ourselves confronting the profound possibility that we are not alone in the universe. The ongoing study of this extraordinary visitor challenges our fundamental notions of life, technology, and our place in the cosmos. Stay with Stellar Tech as we continue following these groundbreaking developments, seeking truth among the stars, and preparing for humanity's next chapter in cosmic exploration.